Most people assume eye color is straightforward. You either have brown, blue, or green eyes, and that's the end of the story. But spend a little time with the actual biology, and you quickly realize that green, in particular, is anything but simple. Green eyes show up in roughly 2% of the global population. That alone makes them unusual. But what makes them genuinely fascinating is that within that small percentage, there isn't one single green. There are multiple distinct variations, each produced by a completely different interaction between light, tissue, and pigment. Today, we're going to walk through those variations one by one, not just what they look like, but why they exist at all. To understand any of this, you need a foundation in how the iris actually works. The colored part of your eye has layers. The one that matters most for our purposes is called the stroma, a fibrous tissue that sits at the front. This layer doesn't contain green pigment. In fact, the human body produces no blue or green pigment in the eye whatsoever. What you're seeing when you look at green eyes is always the result of light behavior, specifically how light scatters through tissue and interacts with small amounts of a yellow compound called lipochrome. That scattering phenomenon follows the same basic physics that turns the sky blue. Short wavelengths of light bounce around aggressively when they hit fine structures. Longer wavelengths pass through. When scattered blue light combines with yellow lipochrome, the resulting visual is green. Adjust the density of the tissue, the amount of pigment, or the distribution of melanin, and the green shifts into something entirely different. Let's start with what most people picture when they think of green eyes, a vivid, saturated, consistent color that doesn't shift much depending on the light. This is the variant sometimes called pure or classic green. The stroma in these eyes is clear and finely structured, which allows light to scatter efficiently and produce a strong blue base. Paired with a solid concentration of lipochrome, the two components produce a clean, unmistakable green tone. There's very little melanin involved, which means nothing is muddying or dampening the result. The color stays consistent because the conditions producing it don't change much. The stroma scatters predictably, and the pigment sits evenly. This is also why it's genetically rare. Getting the precise combination of low melanin, clear stroma, and concentrated lipochrome in the right balance requires a specific genetic configuration that simply doesn't come together very often. Move the balance slightly, add a bit more lipochrome, and reduce the evenness of its distribution, and you end up with something quite different. A green eye with distinct gold or warm copper tones running through it. This variant appears green in lower light conditions, but responds dramatically to direct sunlight, flaring into warmer hues that can look almost metallic. The reason this happens is that when lipochrome is deposited unevenly, it doesn't blend cleanly with the scattered light. Instead, it creates localized patches or streaks of yellow gold that sit visually on top of the green base. The eye looks like it has two separate color systems operating at once. It's not an illusion exactly, it's just that the uneven pigment distribution makes the eye more reactive to changes in lighting angle and intensity. Shift in a different direction, reduce the lipochrome and thin out the stroma, and you move toward the pale or cool-toned end of the spectrum. These eyes can look almost transparent in certain lighting conditions, with a very light, washed-out green that some people describe as icy or ghostly. Because there's so little material in the stroma absorbing or filtering light, almost everything bounces back out. The faint trace of lipochrome is just enough to pull the color away from pure blue or gray, landing it in a soft, cool green instead. One practical side effect worth noting, irises with very low pigmentation let more light through to the retina, which often translates into higher sensitivity to bright environments. It's a direct trade-off built into the biology. Now take the opposite approach. Keep the scattering mechanism in place, but add a moderate layer of melanin on top. The result is what's commonly called olive green. Instead of the clarity and brightness you see in the purer variants, the color has more depth and a muted quality. It doesn't transmit light as freely. The melanin acts as a filter, pulling the overall tone darker and warmer. These eyes tend to look richer and less transparent, sitting at a midpoint between lighter green eyes and hazel or light brown eyes. The shift happens gradually across a spectrum, and there's a wide range within this category, depending on exactly how much melanin is present and how evenly it's distributed. Speaking of distribution, one of the most structurally interesting variants involves melanin that isn't distributed evenly across the iris at all, but instead concentrates heavily near the center. This creates a layered appearance. The outer iris shows the green that comes from light scattering, while the inner ring around the pupil shows brown or gold tones from the localized melanin. The result is sometimes called central heterochromia, and it's responsible for the experience many people describe of their eye color seeming to change throughout the day. What's actually changing isn't the color itself, it's the proportion of the iris that's visible. When the pupil is small, the outer green dominates. When the pupil expands, it covers more of the inner ring and brings the brown or gold forward. The ratio shifts, not the pigment. Moving to the blue-green boundary, there's a variant where the lipochrome content is minimal, just a faint trace, and the scattering mechanism in the stroma leans heavily toward shorter wavelengths. The eye reads as somewhere between blue and green, depending on the environment, the lighting, and even the colors surrounding it. This is sometimes grouped with blue eyes and sometimes with green, which is part of why it's frequently mislabeled. The underlying mechanism is the same as in a clearer green eye, but with so little yellow pigment present that the blue scatter dominates most of the time. External conditions tip it one way or the other. Finally, there are darker green variants, where the stroma itself is denser and thicker than in lighter green eyes. Denser tissue scatters light less freely, which reduces the brightness and intensity of the resulting color. With moderate melanin also present, you get a deep, saturated green that holds its color well, but doesn't project the same luminosity as the purer variants. In lower lighting, these can appear almost brown. In strong light, the green becomes visible again, though it always reads as dark and rich rather than vivid or bright. The density of the iris structure in these eyes also means slightly greater natural protection against scattered light, a functional difference that comes along with the aesthetic one. What ties all of this together is that eye color isn't a fixed property sitting inside the iris waiting to be observed. It's produced in real time every time light hits the tissue. The stroma scatters it, the pigments filter it, the density shapes it. What you're seeing is an output, a result of all those conditions interacting simultaneously. Change the light source and the output shifts. That's why the same pair of eyes can look subtly different in the morning versus the afternoon, indoors versus outside, or next to different colors of clothing. If any of this changed how you see eye color or how you think about your own, let us know in the comments. Which of these variants sounds closest to what you have? And if you want to keep exploring the biology behind things that seem simple on the surface but turn out to be surprisingly complex, subscribing keeps that content coming your way. Liking the video also helps more people find it. Thanks for watching.